Hello guys, welcome to lecture 12, numerical differentiation. You remember from our previous course that we covered differentiation and integration, but that was analytic. So we used the analytic method. So here we just want to look at how we can use numerical methods to solve problems that has to do with differentiation. Again, need to appreciate that differentiation deals with the rates of change. So the rate of change of something with respect to something. So in most cases that we that deals with differentiation or what we face uh, on the ground or in an experiment, what we get are values, not functions or polynomials or mathematical expressions. So many a times, the data set that we get has to do with the numerics. So it is good to appreciate this method of differentiating using numerical values or the numerical differentiation. All right, so we are given this table here and you want to determine the velocity and the acceleration for this table, and then you recall that f of prime of f or df dx, which is the first derivative, is given by f of x plus h minus f of x, everything over h. Right, so using the Taylor series theorem, you have f of x plus h, which is equals to f of x plus f prime of x h plus f prime prime x h squared over 2 factorial plus f3 x h3 over 3 factorial plus and so on, where this O H of 4 represents the error or the truncation error where we terminate our series. So E is equals to O H N is they exist a real and finite value of C such that the modulus of this would be less than or equal to C modulus of h to the power n. E is of order h and E is approaching 0 at rate similar to h to the power 4. So O h to the 4 is truncation error. Alright, so there are three important formulas. We have got the forward difference and then the backward difference formula and then the central difference formula. Alright, so which method is better? How then do we judge which one is better? So this one is forward. As you can see, you have got f of x and f of x plus h. So it's forward if you understand what x plus h means. This one is backward because you're moving to the back. You have got x minus h is backward. And then this is central because it's using both the forward and the backward terms or approximation. So this is given by this table. Let's hope it will illustrate that. For a backward, you have got your f of x situated there, and then this one will be your f of this line. This line, the gradient of this line will be this one and this one. So it's backward because you have got your f of x here, and then here you have got your f of x minus h. And then from here to there, the one that uses this one is forward because you've got f of x and then f of x plus h, and then this one which uses this point, and this one is the central because it uses the extremum points, the extremum points on your interval, these ones. F of x plus h, f of x minus h. So the forward difference formula from the Taylor series of f of x plus h, you get f of x plus f prime of x h plus the error term, and then making f prime the subject of the formula, you get f prime of h is equals to f of x plus h minus f of x over O. Then this will be f prime of x will be f of x plus h minus f of x, everything divided by h. If you divide this one by h, you get O to the power h, because the other h will cancel there. So your truncation error will be to the power order 1 instead of 2. So the backward difference formula, you are now computing the Taylor series for f of x minus h, which is given by f of x minus f prime x h plus the truncation error from this point, and then making f prime of x h the subject of the formula, obtain that, and then making f prime x the subject, which is equals to f of x minus f x minus h everything over h divided by, divide this by h, you get O to the power h, the truncation error there. So this is how we compute or we derive the backward and the forward difference formulas. Let's look at how we compute the central difference formula. So for the central difference formula, you need f of x plus h, which is given by this one, and then f of x plus h, the Taylor series, is given by this one, and then if you subtract f of x minus h from f of x plus h, you will get, so you are subtracting this equation from this one. So this minus this, f of x minus f of x, you get a 0. This one minus this one, but this one minus there to be a plus, you get 2 there. Then this one minus this one cancels, this one minus this one give you a plus, so plus 2 and so on. So you divide everything by 2h, so this one will be okay. So from here you make f of prime of x the subject of the formula, and then from there divide by 2h and truncate from this point going onwards. You satisfy yourself that you get this central difference formula. So those are 3 formulas. You have got the forward difference, you have got the backward difference, and then you have got the central difference. And then we have got higher order formulas. So higher order formulas for higher derivatives. For example, all these ones were working for the first derivative. As you can see, you are computing the first derivative, forward, backward difference for the first derivative. And then for higher order, for example, if you want to compute the second derivative, so you compute the Taylor series of x plus h, which is this one, the Taylor series of x minus h, which is this one, and then if you add these two, you'll get this one, 2f of x. If you add this one will cancel. If you add this one, we'll get 2. This one will cancel, and so on. And then from this equation, you can make your f prime second derivative the subject of the formula, and satisfy yourself that the second order formula will be given by this one with an error term of order 2. So for second derivative, this is the formula. For third derivative, use this one. For fourth derivative, if you want to compute the fourth derivative, we use this one. Alright, so let's look at an example. So we want to use the forward, backward, and central difference approximation to estimate the first derivative of f of x, which is minus 0.1x to the power 4 minus 0.15x to the power 3 minus 0.5x squared minus 0.25x plus 1.2, where x is equals to 0.5, and the step size is that you want to use is 0.5 and 0.25. Note that the derivative can be obtained directly. So if you differentiate this, you get this function, and the true value for this function is given by minus 0.9125. So in this example, the function and this derivative are unknown. How about if this function is not unknown? So that's the case of the table. So how about if you are given a table? So what makes life easy is that the function, you are given the function, and then you can compute the derivative. So you can compute the value of the derivative of those points. But how about if the function is unknown? So the solution will be, for the step size of x is equal to 0.5, we use the forward difference method. So the forward difference method will be f of 0.5, which is given by 0.925, and then you will need, if this is f of 0.5, you will need the next step going forward, which will be the f of 1, which will give you f of 1, which is 0.25, and then the center one, which is more like f of x, which is 0. So for this formula, it is important to note that this is more like f of x naught. So this is f of x naught. This is f of x naught. This is f. No. Sorry for that. This is f, this is f of f1, f2, x2. So your x naught is 0, x1 0.5, x2 0.115. So the forward divide difference formula will be given by f prime of this will be given by substituting these f values on your forward difference formula. You know that this will be f of f of this will be f of x2 minus f of x1, everything divided by 0.2, because you want to estimate the value of f of x 0.1. And then the backward difference formula is given by the backward formula, which is given by the backward formula is given by f of x minus f of x minus h, which is in this case f of 0.5 minus f of x naught, everything divided by 0.5, which is minus 0.55. And then the central divided difference method, which is given by f of x plus h minus f of x minus h. So we are now using the extreme values, this one and this one, this one and this one, yes. So this is the upper one, x2, f of x2 minus f of x1 over the step size, which is 0.1, because from 0 to 1, the difference is 1 in terms of x. Step size there is 1, so solution there is 1. And these are your respective errors. So the true value minus the error divided by the true value. This is your error, this is your error. The true value minus your error divided by the true value minus error. Remember how we computed the absolute error. These are absolute errors. Make sure you always compute the absolute error. So you can practice, do the same for the step size of order, 0.25. So for both the forward and backward difference, the error is OH, because this is first order differentiation, and halving the step size H, approximately half the error for forward and backward difference formulas. And then the central difference for approximation formula is more accurate than the backward and the forward difference formula, and the error term is given by OH squared of order 2, and halving the step size H approximately quarters the error of the central difference formula. Thank you.